Well, welcome back to RDWorks Learning Lab. You can see in front of you the subject for today. We're going to take an in-depth look at how this power meter works, possibly suggest to you that you could make your own with a little bit of help. I have to say that this has probably been the single most important piece of equipment that I've ever purchased. It has helped me through understanding so much about my machine, where the problems are, where the power losses are, whether or not I'd bought a tube with the right power. It's just been such a marvellous tool. Okay, I paid a lot of money for it. I don't regret it. But a lot of you guys, I think, are resistant against spending $300 for what basically looks like a meat thermometer with a lump of metal glued to it. Technically, that's not a bad description. In reality, it's quite a lot more than that. It's not something that's easy for you to make. And what I need to do is quickly explain why that situation exists. Measuring infrared watts out of our machine is a bit of a difficult concept to grab hold of when you can't see the heat and you don't know quite what it's doing. So I'm going to try and describe to you in very visual terms how this meter works, and then you'll understand why maybe it's a difficult thing for you to try and manufacture for yourself. Welcome to my science laboratory. Now, you might think this is a stream of water, but in fact it's a steady stream of infrared energy. It's probably equivalent to about, say, 20 watts, but it's flowing out of my laser tube, and what I'm going to do, I'm going to collect it in a calorimeter, which is the standard way of measuring power from things. And a calorimeter is basically, here we've got what looks like to you a milk bottle. In reality, it is an aluminium block. Why aluminium? Well, aluminium has got a very good heat transfer capability, and it very quickly evens itself out throughout the block. And then what we've got on here is a digital thermometer to measure the amount of heat or the temperature by which the block is being raised. And the block is raised by a temperature proportional to something called its specific heat, which is its ability to absorb energy, heat energy. So this temperature is a measure of the energy that's going in. Now you'll note that the calorimeter is sitting at 1 or 10 at the moment, 10 degrees. That's, let's call it ambient room temperature. Unless you go to some extreme lengths to force the temperature of the calorimeter down, it will always have a base temperature of some sort. So what we're now going to do is to run our steady stream of energy into the calorimeter for a fixed period of time, and that's the important thing. We're running the heat energy into this aluminium block for a specified period of time, and let's assume that that's the specified period of time. Now at the end of that block of time, we can look at the temperature rise, and it's gone from 10 to 90. That's a rise of 80. Now that rise is equivalent to the amount of heat that's stored in that block. Very simple. That's what calorimetry is all about. The first question is this a calorimeter? Well, not really. You can't use standard calorimetry rules to work this thing out. Why not? A couple of things I want you to remember. First of all, when we looked at reflectance, remember we looked at aluminium, natural aluminium, and it had got a very, very high reflectance. So if we use an aluminium block as a calorimeter or as a means of absorbing heat energy, the first thing that's going to happen is this. It's not going to absorb it because most of it's going to be reflected off. So that's no good. So what we need to do is to destroy the crystal structure on the surface of the aluminium, which is the cause of that reflection. And we do that by oxidizing the surface. Now there's a special process of oxidation called anodizing, and depending on the process that you use, the depth of anodizing can vary. Anodizing, or aluminium oxide, has got two very interesting properties. Number one, it is highly absorptive to infrared radiation. I say highly, I didn't say 100%, because I haven't been able to find out exactly how much energy is absorbed by anodizing and how much is reflected. But we have to assume that it is not 100%. And the other thing about anodizing is that although it's only probably maybe 25 microns thick on the surface, it has only got about a quarter or a third of the heat transfer capability of aluminium itself. So getting the heat into the block is being slowed down by the one thing that you're using on the surface to absorb the energy. So it's a bit of a catch-22 really. So what I'm going to try and do now is to simulate that process by putting some holes in the top here. Now, I don't know how many holes I've put in the top there, or what percentage of the heat is going to be reflected. It's an unknown. Let's try it again. And yes, we're starting to fill up. But hey, something else is happening. As the water level goes up, look, that stream that's leaking out the side is getting bigger and bigger and bigger. That's heat loss. The bigger the temperature difference away from ambient, the greater the heat loss from the block. That's not a calorimeter, that's an unknown quantity. It's always the same because that flow will be directly proportional to the temperature difference above ambient. And as you can see, as the water level drops down, so the leakage decreases. Another serious unknown. And what you're looking at there is basically the equivalent of what I'm holding in my hand. A temperature gauge, a block that has got an unknown absorption capability and it's got no protection around it, so it leaks heat away as you put it in. That's an exact simulation of what this device is. So why does it work? Well, the answer is it all depends on constancy. You have to be consistent in everything that you do. So the first thing you must do is always start off from ambient temperature, and then you put a fixed amount of heat into the unit. You don't worry about this reflection and you don't worry about that leakage. What you do, you run it for a set period of time again, and it doesn't matter what that time is, but it's a fixed period of time. And at the end of that fixed period of time, you say, right, what's the temperature? It's 60. Well, it started off at 10 and it's now 60. So that is 50 degrees temperature rise. Now, whenever I put this flow into this container, this measuring system, this comparator, it will always read 60 degrees or 50 degrees above wherever ambient you started from. But it is important that you start from ambient and that you don't start off at, say, 20, because look, here we are at 40 degrees and we've got some leakage. Now, if I started off at 40 degrees and the ambient temperature was 10, I've already got an unknown quantity of leakage. It's not the same constant conditions, so you must keep all your conditions constant all the time. And the calibration, and we'll come on to calibration in a second, which is the relationship between this flow, which we don't know, and this temperature, which we do know, has got to be related by some calibration system of some sort. So here we have an international standard measuring system of some sort, which is very, very accurate. And what we can do, we can put this flow, this energy that we don't know what it is, and we can put it into this international standard, and we can measure it for a certain period of time. And then we can stop, and the international standard says, 40 watts. So that's 40 watts. But 60 was 40 watts on there. So whenever we see 60 or a difference of 50, that equivalent of 40 watts. So all we've got to do is to test this at different flow rates, energy flow rates, and relate this scale to some absolute standard. And then we've got a relationship. We have a comparator, not a calorimeter. And that's what this thing is. It's a temperature comparator which has been converted into a scale which reads watts. Once you've related those by a calibration chart, you've got a very accurate piece of instrumentation. Look what arrived through the post today. A little yellow peril. In fact, what it is, it's a digital thermometer all the way from China with a K-type thermocouple and another K-type thermocouple. 2 thermocouples and an instrument for £10. Ridiculous. I get a digital thermometer which tells me that the air temperature outside at the moment is around about 9 degrees C. It changes from C to F to K. We also have a max min button and an average button, which is great. The max is the most important bit that I'm interested in with this unit. Now these K-type thermocouples have got very, very predictable performance. Wherever you buy them from in the world, they will perform the same to within a couple of degrees across the whole of the range, from probably something like about -100 up to about +1300, I think it is. It's a staggering range that they work over, and they're pretty linear over the whole of that range. Why was I so excited about getting a digital thermometer? Now, I bought this through eBay UK with its K-type thermocouples. It was a silly price. Now, what I've designed here is something that looks like a lollipop. And in fact, I'm going to call it a doHICky, because there isn't a real name for it. It's a well-known phrase in America and probably throughout the world. It's a slang term for something that you don't really know the name of. You can't think of a good name for it. So that's exactly what this is, a doHICky. But in the middle of the word is HIC, which stands for what I would like to call Hobbyists Infrared Comparator. And that's what this is. It's a comparator. Now, it's a comparator that will allow you to measure the power of your machine. How's it going to do that? Yeah, here you ask. Well, I've already described how a comparator works. We need to have something which is stable, and then we need to reference it to something that we know. And I'll just go through exactly what I've been able to do to get to this stage. So the first thing that we're going to do, we turn this lump of metal, which is black anodized aluminium block, with a piece of stainless steel tube as a handle. Now, what I'm going to do is just thread a piece of 5x1 polyurethane tube over it to start with, just as a strain relief, as you'll see in the end. And then I'm going to thread this down the centre of this piece of 4mm stainless steel tube. And I can hear that it's reached a stop position. Now hopefully that stop position is right in the centre of here. And if that is the case, which it should be because that's where I've machined it to, I'm going to drop a little slug of aluminium in there. And that slug of aluminium is going to be held in place by an M3 grub screw. And so when I tighten this up, the aluminium plug will be pushing on the bulb at the end of the K-type thermocouple, and then the thermocouple will be locked in place in the centre there and mechanically connected to the aluminium slug. We will then slide this forward and just push it over the handle a little bit. That way we've got a little bit of strain relief on this cable. Right, there's just a piece of ordinary 5x1 polyurethane tube. So now we have here the elements of a comparator. We've got a block of aluminium which has been anodized and will absorb some of the heat that's fired at it, some of the infrared radiation that's fired at it. How much we don't know, but it doesn't matter. We've got a means of measuring the amount of heat right in the centre of that block with our K-type thermocouple. All we need now is a known power source so that we can start to calibrate this. It just so happens that I now have a very nice 60-watt tube in this machine, and using a piece of equipment that you'll be familiar with, I shall quickly hide that away, I've generated this curve of percentage programmed against power output. So now I have got a standard that I can test power into this particular device. I have the opportunity now to calibrate this device against a power source that I already know. I'm now going to demonstrate my faith in two pieces of equipment. First of all this, and secondly the machine, because what I'm going to do is totally at random stop somewhere here, and that says 56 watts, sorry, 56%. Now 56%, if I follow it up, says I'm going to generate 67 watts. So we're testing two things that work here. Number one, I haven't had my machine on at all today, so this is from stone cold. We're going to start the machine up. We're going to check whether or not the calibration chart is anywhere near accurate, and find my spiral program, and we want to set it to 56%. So we're now ready to run a 56% test to check out our meter. And just as we walk round to the back of the machine, I will just show you my my little tube cover. And here I have a bucket of water which has been sitting in the workshop, and it should have assumed an ambient temperature by now. It's been here several days and it should be tracking the ambient temperature. I'll just stir that around for about 30 seconds. And I'm going to do all this live so that you can see how long it takes me to carry out the test. Now, I thought it was quite quick. There we go. Now that's a previous 0 that I already had set on there. And as you can see, it's not far off, because it's still quite cool here in the UK this time of the year, even though it's a nice sunny time at about 1 o'clock in the afternoon. So it's the warmest part of the day, really. So we now set that to 0 just before the test, and it should, and away we go. Now the test has started, but as I said, I'm not worried because I've got 10 seconds before the power comes on. Okay. And we're expecting to say 67 watts. .67 67.8 watts. Okay, that was a fair test from cold, wasn't it? Tested both the tube, the machine setting, and this piece of kit. Everything is nice and consistent. Now, to make this a fair test, a fair comparative test, look, it's still up there at 60, so what I really ought to do is bring that back down to 0 again. And it's going to take 30 seconds or more stirring. And there we go, we're more or less there, not quite, but by the time we've wiped it down. And wiping it down is a bit of an arduous task actually, because this has got a matte finish anodize on it, it doesn't want to dry very easily. You have to be quite careful with it, and because it's square or rectangular, so it's got all these square corners that you've got to get into to take all the moisture off of it. And even now it looks dry, but I can feel that it's actually got a film of moisture on the surface. But there we go, look, we're more or less back to 0. And that took what, half, 3/4 of a minute to get that back to 0, ready for the next test. We'll now go through the same procedure with this little animal here. Okay, so look, I've just done a test, and what I'm going to do, you must, after you've done a test and made note of your reading, turn the meter off. Stir it round in the pot for about 15 seconds, that's all it will need. And a quick wipe off, because it's a nice shape to wipe off nice and easily. And then we need to turn the meter on, because turning the meter on will reset, and it's 9 degrees C. We'll press the max button now, which I've made red because it's easy, 9.1, and we'll run a test. So we've got to remember one number only, which is 9.1 degrees. In fact, to make it easier for my maths, I'm going to make it 9.0. Now you'll note the temperature's climbing, and I just stop. I don't have to wait for it to go and reach a maximum this time. So 53.8 minus 10, which is 43.8, plus 1, which is 44.8. So the difference was 44.8 degrees C. And I will now bring in a calibration chart. And when I look at calibration chart, in the green column where it says 44.8, what have I got? I've got 69 watts. Now that's moderately impressive, I thought. I'm sure there's a lot of people out there that would like to have one of these pieces of measuring kit, but not at the price they charge for either the cheap one or the expensive one. Now this has got several advantages over that. There are no mechanical moving parts in there. Now one question I can hear quite a few people asking, especially when they get one of these and they say, oh, that's not shot blasted. It's not a rough finish. Well, here's one that I produced with a rough finish. Two problems with it. Number one, when it's wet, it holds the water just like the other meters do, and you get this film on the surface which is not dry. It takes quite a lot to get it dry. So that's one of the good reasons why you wouldn't want a matte surface. And number two is, with all the work that I've done with both of these devices, and in fact these are not the only two that I've got, I have in fact got 4 of them, 2 matte and 2 normal machine surfaces. They both perform more or less the same, but the spread of results with the matte one is slightly wider. In other words, this one gives slightly more reliable results. I've not staged any of this at all. I've done my calibrations completely separately. I spent quite a reasonable time producing this calibration chart for the machine. Now these two things, bearing in mind this is now a known standard power, and I can therefore relate temperature to power. When you use this device, make sure you always have your beam perpendicular to the surface. If you angle it, there's a chance that you will get some reflection off of the surface. To make one of these, as I said, is quite an expensive thing to do if you want to make one for yourself. I'm planning to make a batch of 50, and for a batch of 50 I think that I can make these for around about £25–28 each with my time. But by the time I put postage and packing on to get it anywhere in the world, I've settled on a price of £30 British. Now that way it will arrive with everything that you need except this, which you will have to source yourself. Now there's two good reasons for that. Number one, this is free shipping and it's dirt cheap. There's no point in me getting it from China and sending it to you when you can get it to you for free directly from China. And the second thing is, I won't be selling you an instrument. I shall only be selling you a piece of metal. So there's no fear that I'm treading on anybody's toes. This is like a recipe that I'm giving you here, and you've got to buy some of the ingredients yourself, and I'll provide you with some of the ingredients, and then you can go away and bake your own cake. I will PDF the calibration chart to you, and I will send you the files both in DXF format and in RLD format so that you can run the program that matches this calibration. Now I hope that that looks like a reasonable deal, and if it is and you wish to participate, go to the messaging system. Even if you've already sent me something already and I have your email address, please do it again through the YouTube personal messaging system. That way I will have a record of everybody that wants to buy one of these, because at the moment I've probably got to spend the next couple of 3 weeks making a batch of 50. I've got pieces organised and underway, but I don't have all the material here at the moment. So when it comes to time to post this, I will send you a request for payment, which you can fulfill via PayPal. You don't need a PayPal account, you can just pay it on your credit card into PayPal, and then I will ship it to you. You will need to send me your postal address in response to the payment that I ask for, and I will ship it to wherever you are. As you can see, it's very compact. It will only be in a very small mailing envelope, and the mailing envelope will say that it's a gift of zero value. It's a metal sample. So just to remind you to finish with, we decided we were going to set the machine to 56%, where I was aiming for 67 watts. In fact, when I measured it, it came out at 68 watts. And then when I used the DoHICky to measure the same thing, the result came back as 69 watts. It might not be entirely accurate, but it's certainly good enough for doing what most of us want to do. And in fact, I find this so easy to use that I'm going to put my Mackenmeter away in a drawer for occasional use, and this is now going to become my everyday favoured piece of equipment because this is so easy to use and it's pretty durable.